So we're talking here about, in section 4.1, about extreme values of functions. So our definition of an extreme value, let f be a function with a domain D, then f of c is a, the absolute or global maximum value of f on D, if and only if f of x, all the other values of x are less than or equal to f of c for all x in the domain. And it's an absolute or a global minimum if that value of f is greater than or equal to, is less than or equal to all the other values of x in the domain. Now notice in our definition here, then we're talking about f of c. It is the maximum value of f or the minimum value of f. It is not an ordered pair. It must be given as a y value. Now, because of that, if we look at some different examples here, so in the green, we see an example of a sine function, and its domain is all real numbers. So it's that sine wave that goes on forever in each direction. So the largest y value that the function takes on is going to be 1. And it's true that it takes it many, many different times, in fact, an infinite number of times. But that's okay, because it's only asking for that y value. So the absolute maximum for this function is going to be, remember, it's a y value, is y equals 1. And similarly, the absolute minimum, or global minimum, is that smallest y value that the function ever takes on, and that is going to be -1. And the fact that it reaches that smallest value an infinite number of times is not really relevant. It's just looking for that largest and smallest value. Now, if we look at a parabola that opens down, say 1 minus x squared, you can see this has a largest value, so the absolute maximum here is going to be y equals 1. Notice it happens to occur, as did these others, at a place where the derivative is going to be 0. Now, in terms of an absolute minimum, if we are on a domain that's all real numbers, because this goes forever down, there isn't one. There is not a smallest y value. So some functions will have an absolute maximum and an absolute minimum. Some might have one but not the other, or it's possible it could have neither an absolute maximum nor an absolute minimum. It's going to be a combination of the characteristics of the function, but also domain plays a role in this. So if we look at this next one, we see that on the red function, f of x here, that is going to have a largest y value here. That's going to be 2, so the absolute maximum is going to be y equals 2, and the absolute minimum is going to be that y value. That's supposed to be at -1. It doesn't really look like it, of -1. But notice, what if we change this and say, suppose this is an open circle at each endpoint there instead of solid dots? Then you can see in this case that there is no maximum and there is no minimum. So the domain plays a role in this. Now it really gets strange on the yellow function here, because remember, the maximum value means it has to be greater than or equal to all the other values of y. Well, all of the y values are 2. So you could correctly say that the absolute maximum is y equals 2, because 2 is greater than or equal to all of the other y values. Yes, that's true then, that it is also an absolute minimum, because it is also less than or equal to all of the other y values. So a strange case indeed here, where the absolute maximum is equal to the absolute minimum, but that can only happen when you have a horizontal line. So moving on to the white here, the extreme value theorem. This is an important one, a named theorem. And so we need to make sure we consider the conditions, what part of the hypothesis there, as well as the conclusion. And so this is trying to tie together here the role that the function and its domain play in this. So if f is continuous on a closed interval, then under those conditions, f will have both an absolute maximum and an absolute minimum. Now, if either of those conditions are violated, if the function is not continuous, or if it's not a closed interval, we may have an absolute maximum and or an absolute minimum, but we won't be guaranteed one. And in some cases, we won't have one. So be careful. Okay, so here now we move on and talk about relative, or what's sometimes called local extrema. So now we're talking about a relative maximum or a relative minimum. And some authors of some books like to use the word local. So a local maximum or a local minimum means the same thing. Now, we have, we're going to kind of talk about two different kinds of points here. The interior points, that is the ones that aren't the endpoints, and then we'll address the endpoints separately. So in the white here, we say, let C be an interior point of F. So on its domain, it's not an endpoint. Then notice we're going to say the ordered pair C comma F of C is a relative maximum if and only if it is greater than or equal to all of the X values in some open interval around C. So it doesn't have to be the highest mountain in the whole range. It just has to be at least a little mountaintop, a top of a hill at least. So it's the largest Y value in some little region around it. And similarly for a relative minimum, it's going to be the lowest Y value, the smallest point in some little region around it. Now, different authors treat endpoints differently. So some authors don't allow endpoints to be relative minima and relative maxima. The author of our textbook does. So if that endpoint is the lowest or the highest point in some region containing it, then it is going to be considered a relative minimum or a relative maximum. And if not, it won't. So the writers of the AP exam know and understand that different authors treat endpoints differently. So they will never ask you, is an endpoint a relative minimum or a relative maximum? But by our definition, by this definition, the definition of our authors in our textbook, then an absolute maximum is always going to also be a relative minimum or maximum too. So in this curve that we see here, you can see that there is a relative, I'll say a relative maximum we're going to see at this point right here, that ordered pair, and also at this one. And you can see that in this, the first one, there's going to be a derivative of 0, and in the second one, you're going to see a derivative that's undefined. Now, we're going to see relative minima. That's a lowest point in some region, and so are each of these endpoints. So those are each relative minima. And so you can see one that has a horizontal tangent, and these other two get to be relative minima because they're at the endpoint and they're the lowest point in some region containing them. So in the blue here, we see a theorem, and I don't think this is all that earth-shattering, but it says if f has a relative maximum or minimum at an interior point, and if the derivative exists there, then the derivative is 0. Well, that's nice, but remember we can also get relative minima and relative maxima at places where the derivative is undefined. Okay, and those we'll call critical points. Any place where the derivative is either 0 or undefined is going to be a critical point. So I'm going to say CPs are going to be where f prime of x is equal to 0 or f prime of x is undefined. And that's really, I think, a little more valuable and a little more universally useful. Okay, here's the big one, the candidate test for absolute extrema. This is really important, and I'm not really sure why, but students struggle with this mightily. So it tells us now a way of finding absolute maxima and absolute minima. It's a prescription. It's a strategy to employ. So first, we're going to find the critical points. That is, we'll find all the values of x that make the derivative 0 or undefined. So it's just a list. Then we will plug in those critical points, those values of x that made the derivative 0 undefined, into the function f, along with the endpoints. Then we'll look at that list of y values that we got by plugging those in. The largest y value is the absolute maximum, and the smallest y value is the absolute minimum. So let's see what this looks like. Here's an example. We have a function. You might recognize that as a parabola that opens down, and we have a closed interval domain, -1 to 2. So and we're going to try to find the absolute extrema. So I'm going to say find. So absolute extrema, that word extrema is plural for extreme points. And so that's a way of just generally saying find the absolute maximum and the absolute minimum. So we will start by taking the derivative, which is 2x, and setting that equal to 0. And we see that that's going to be at 0. So this we will call a critical point. There is no place where the derivative is undefined, so that's our only critical point. So now what we're going to do using our candidate test, we're going to evaluate the function at 0, and we're also going to evaluate it at the endpoints. And so what we're looking for here is what is the largest y value out of these candidates. So the largest and smallest y values must come from these candidates. So plugging that into the original function, f of 0 is 1, f of -1 is 0, and f of 2 is -3. So that means that y equals 1 is the absolute maximum, and y equals -3 is the absolute minimum for this function on that interval. Okay, let's look at the next screen. So here we have now a new example. We're going to find the absolute extrema for this function, g of x equals x minus 1 to the 2/3 on the interval from 0 to 9. So we are using our candidate test. So we're going to start by finding the derivative. And you're going to get 2/3 times x minus 1. We subtract 1 from that exponent to get -1/3 times the derivative of the inside function is going to be just 1. I'm going to write that in radical form. I think it's a little easier to evaluate. So the 2 from the 2/3 goes on top. The 3 from the 2/3 is going to be in the denominator. The negative exponent is going to kick the x minus 1 into the denominator. And I'm going to write that 1/3 power as the cube root of x minus 1. So here is our g prime of x. Now we're looking for where is the derivative 0 or undefined. Well, fraction is equal to 0 when its numerator is 0, but our numerator is always 2. So there are no values of x that make this equal to 0. A fraction is undefined when its denominator is 0, and so our denominator will be 0 when x is equal to 1. That makes x equals 1 a critical point because it makes the derivative undefined. So now using our candidate test, we're going to evaluate the original function at 1, and we are also going to evaluate the original function at the endpoints, g of 0 and g of 9. So into the original function, 1 minus 1 is 0. 0 to any power is 0. Plugging in 0, we get -1. -1 to the 2/3 power means we're going to take the cube root of -1 and then square that. That gives us a +1. When we take 9 into that original function, we're going to get 9 minus 1 is 8, and 8 to the 2/3 power, we're going to get the cube root of 8 and then square that result, and so that is going to be 4. So after we have plugged in all the critical points and the endpoints into our original function, we have the candidates for absolute maximum, maxima, and minima. So we can see that the largest value is going to be 4. That's the absolute maximum. And we see the smallest one is 0, and that's going to be the absolute minimum. Notice we're giving them as y values. Okay, so now we turn our attention to this piecewise function here. Now, there's a lot to think about here. First, we're going to look for relative extrema. So we're going to consider the left branch, the right branch, and then where the two functions come together, because we can get critical points from any of those regions. So first, looking at the left branch, we're going to take the derivative of x squared minus 1 and see that that's 2x. We're going to set that equal to 0 because we're looking for critical points. And so we can see that x equals 0 is going to be a critical point, and that is on our domain because it is less than 1. So that's one of our candidates so far for a possible relative extreme point. Now, we're going to take the derivative also of the negative x plus 1, which is negative 1. Now that is not equal to 0 anywhere, so there are no critical points that are going to come from anything greater than 1. So we're not getting anything from this part of the domain. Now we also have to consider where these 2 points come together. So let's see what happens. On the left side, when we do, so I'm going to take that left-hand limit. If we plug in 1 squared minus 1, we get 0. On the right side, we're going to get the negative 1 plus 1 is also 0. So if we can imagine what this graph is looking like, we're getting this parabola that opens up and has a y-intercept or has a vertex at negative 1, and as it approaches 1 here from the right, it's getting closer and closer to a y value of 0. Then that joins this straight line, which happens to exactly connect to that, and then has a slope of negative 1. So what we're seeing here is that it's continuous at this point, x equals 1. We can see that from our graph that is the highest, the largest y value in some region around there containing it. So that, because it's going to be a corner point, so that is going to be a critical point, I should say that. So then for our relative extrema, we're just looking for points that are going to be the largest or smallest in some region containing them. So certainly at x equals 0, that's the lowest point in that little region containing it. So that means when we plug in 0 into that part of the function where it's defined at x equals 0, that's going to be negative 1. That will be a relative minimum. And when we plug in the 1, we get 1, 0, and that is the tallest point in that little region, so that will be a relative maximum. Okay, now let's consider the b, what's going to happen here for absolute extrema. So if we evaluate this function at negative 1, that's going to have to go into this branch right here. We're going to get negative 1 squared minus 1 is going to be 0. When we plug in that endpoint 2, that's going to go into this branch. That's going to be a negative of negative 2 plus 1. And that is going to be, oops, I think I drew my graph wrong. That's going to be a positive 3. I think, am I doing that right? No, I'm not. So I'm plugging in a positive 2. I didn't look right on the graph. So that's actually going to be a negative 2 plus 1, which is negative 1. we have our two critical points, which we already evaluated. We know that f of 0 we said was -1. We found that earlier, and that f of 1 is equal to 0. So we can see here that we have 1, 2, 3, 4 different candidates to be an absolute minimum or an absolute maximum. Now you can see that 0 appears twice and -1 appears twice. That is not important. That doesn't really matter. But we can see that the smallest of these values will be the absolute minimum, and the largest of those will be the absolute maximum. All right, a lot to take in there.